introduce Adrienne Erickcek. So Adrienne did her undergrad at Princeton and her PhD at Caltech, followed by a stint as a postdoc at the Perimeter Institute, where I just missed her. I was there about a month after she left. And now she has been recently promoted to be a full professor at UNC Chapel Hill. Adrienne was also recently awarded an APS fellow for her theoretical contributions spanning cosmology, including inflation, cosmic acceleration, and dark matter, with a key focus on understanding primordial density perturbations on small distance scales. So yeah, thank you very much, and we'll be hearing about dark probes of the early universe.
Hello, everyone, and thank you so much for the invitation. I'm really happy to be here today. It's my first time in Rhode Island, so it's a lovely day, and I've really been enjoying talking to everybody here. I'm a cosmologist, so it is like mandated that I start with a timeline of the universe to get everybody oriented on the history that we're talking about here. So, roughly, not at all to scale, illustrative purposes only, the universe's evolution follows a trajectory of different periods of domination. And what I mean here is what is dominating the energy density of the universe. So right now, we live in a cold universe that has a temperature of 2.7 Kelvin, or 10 to the minus 4 eV, 13.8 billion years after the Big Bang. The beginning of our clock, as far as I'm concerned, is the end of inflation. I'm not going to talk too much about inflation today, or how it got started, or how long it went. Those are all very empty and open questions. I'm going to say time equals 0 is the end of inflation, when the temperature, we don't know exactly what it was, but something as high as 10 to the 16 GeV. Then, the next major benchmark that we have to work with is the period of neutrino decoupling and Big Bang nucleosynthesis. And this was a process that spanned, a couple of minutes after the Big Bang, temperatures between 3 MeV and down to 0.07 MeV. This is going to be one of the major pillars, and we'll talk more about this. The next major event in the history of the universe is matter-radiation equality. So this happened at about 51,000 years after the Big Bang. And this is the point where the universe went from being dominated by relativistic particles to being dominated by non-relativistic particles. Shortly thereafter was the release of the cosmic microwave background. That's when the universe became transparent for the very first time. And that happened 380,000 years after the Big Bang, and now a temperature of 0.25 eV. That's when atomic hydrogen was able to form and survive for the very first time. And the final transition that we have is matter lambda, matter dark energy equality. This just happened, 4 billion years ago, and this is now the start of accelerated expansion and a period where we are now dominated by dark energy. So this is kind of the historical timeline. These are the major events we're going to be talking about today. In particular, the eras we're going to focus on today is this period here between the end of inflation and neutrino decoupling, and I call this the gap. This is the cosmological gap. We have virtually no probes of this era, and as a result, we have very little confidence about what happened here. So we call this the gap, the cosmological gap. And then we have generally fairly confident we understand what happened between Big Bang nucleosynthesis, and my pointer is giving out, even with new batteries, so something's more wrong there. We have a period that we think that we thought we understood pretty well, but I'm going to test that a little bit. How well do we really understand this period between neutrino decoupling and Big Bang nucleosynthesis? And this is where I will say to the if the tech people are listening, if you have a different laser pointer, mine seems to be on the fritz, even with new batteries. Okay, so we're talking about evolution of the universe. We have to set our clock. And the clock that I want to use is the expansion of the universe. That is the cosmologist's favorite clock. And so when we talk about the expansion of the universe, what we're talking about here is imagine laying down a grid in all directions without boundary. My grid here does have boundaries, but that's because I'm just limited by real estate on the slide. When we talk about the expansion of the universe, what we say is that the various galaxies stay at their respective grid locations. That's what we call their co-moving positions. And then we have a grid lines that are growing in separation. So this is what we mean when we talk about the expansion of the universe. And the way we parameterize this is the physical separation between any two objects is their co-moving distance, that is how many grid cells they're separated by, times the scale factor A, that is basically going to be the horizontal axis on most of the plots I show today, that characterize how far these grids are apart from each other. Oh, thank you. Thank you, thank you, thank you. Okay. There we go. Okay, power. And so these grids, as we go through in time, these grid lines are growing away from each other. And that's how you should think about the expansion of the universe. And so when you see the scale factor A, that is a fraction of, for any two objects, A equals 1 is today. And then, say, an A of, a half is saying that the objects are half as far apart as they are today. Now, the way we observe this is via cosmological redshift. So the redshift here is the change in lambda over lambda. It's just given by the inverse of the scale factor. So the value today divided by A. And so we can use this to basically map out the expansion of the universe. And we characterize the expansion of the universe via the Hubble rate, which is 1 over A dA dt. So this is parameterizing how fast, it's a rate, how fast is the universe expanding. So this is basically to orient you on how I'm going to track the passage of time. Now, the contents of the universe determine how the expansion rate changes. This comes from general relativity. It's my favorite equation, that the expansion rate squared is just related to the energy density of the universe. Now, what is the universe made out of? Today, the universe is made out of 69% dark energy. We do not know much about this stuff, but we know its energy density is basically constant as the universe expands. This is why it sometimes goes as the name vacuum energy. It is the energy associated with empty space itself, and so you get more space, you get more energy. So the energy density stays constant. 31% of the energy density today is matter. Matter dilutes. So as the universe expands, the matter density just goes as 1 over volume. And so as we go through time, the matter density is falling as 1 over A cubed. And then today we have just a very trace amount of radiation. The radiation density, however, scales as 1 over A to the 4. And that's because the number density of photons goes as A to the minus 3. Number density tracks as 1 over volume. But then each photon is losing energy due to the cosmological redshift. And so the energy density goes as A to the minus 4. Which means even though radiation is way down here today, in the early universe, it was the dominant component. And this picture shows why we have those eras I talked about before. Radiation domination giving way to matter domination, giving way to dark energy domination. So history of the universe, another timeline. Here we are today where we have planets and stars and black holes and people. And we go back in time to higher and higher temperatures. And that first benchmark I want to talk about is Big Bang nucleosynthesis, 2 to 3 minutes after the Big Bang. This is where protons and neutrons fuse into helium and deuterium. Mostly helium, trace amounts of deuterium left over for the ride. And that happens here. Everything before this is entirely hypothetical. So let's talk about Big Bang nucleosynthesis. We're about 200 seconds after the Big Bang. This is the mass fraction of atomic matter as a function of the proton-neutron density today. These curves are the theoretical curves. The yellow boxes here are observations. Observations of primordial deuterium, observations of primordial helium. And so where these theoretical lines intersect the yellow box, you can read off how much protons and neutrons we've got, and it's about 4 to 5% of the density of the universe today. Now, remember I just told you that that matter makes up 31% of the energy density of the universe today, of which only 4 to 5% is protons and neutrons. The rest of it is the dark matter, that we don't know what it is, but it's not just that it's dark. It's not like it's just dust or rocks we can't see. It is fundamentally not on the periodic table. It is something other. So dark matter, it's more, it's not just ordinary matter that doesn't emit light. It's something that's outside the realm of chemistry. It's off the periodic table. No known particle fits what we need it to be. Next major benchmark that I want to talk about is the cosmic microwave background, 380,000 years after the Big Bang. Now the universe has cooled to a temperature of only 3,000 Kelvin, and atomic hydrogen can form for the very first time. So we end up with atomic helium and atomic hydrogen atoms. The light that was present, the photons that were present up to that point, were constantly scattering off the free electrons. But once all the free electrons get swallowed up into atoms, suddenly those photons can start traveling on straight lines, which they do for the next 13.8 billion years. And we see them as the cosmic microwave background. So this is the Planck satellite's picture of the cosmic microwave background. The galaxy has been removed here. This is the theorist's picture. The gray outlines here are the parts that are usually masked from real science, because what's going on in here is a reconstruction based on the rest of it. The galaxy really obscures our view here. These hot spots and cold spots, and I swear this is the only time in astronomy that red means hot. These hot spots and cold spots vary by a few hundred microkelvin from the average. So the CMB is incredibly uniform, and at 1 part in 100,000 fluctuations. So with microkelvin fluctuations on top of a uniform background. Now, this is pretty, but this isn't how we look at it. We look at the CMB as a power spectrum. So what this is it's saying, let me take my detectors and let me separate them by a certain angular scale. Cosmologists have the annoying habit that we always plot our figures large scales to small scales. It's always backwards. That's universal. So large scales, large angular separations are always going to be over here. Small scales, small angular separations are over here. And then these points are just asking, if I take measurements with those angular separations, how much correlation is there between those points separated by those angles? And what we see is a very complicated feature of these peaks and ringing. These are acoustic oscillations. The red here is the data points. The green is a theoretical model corresponding to a universe that contains 69% dark energy, 26% dark matter, and 5% atoms. And it fits very well, and we're very pleased with ourselves. But how well do we really understand the evolution of the universe between these two benchmarks? And so as a first pass of a test, to try to quantify this, I'm questioning the conventional wisdom that it's just radiation giving way to matter domination. What if there was something else? And this is work that was led by my graduate student, Alex Sabatka. We put in a massive particle. So this blue here is a massive particle. So it's redshifting away slower than radiation, but then it decays. So this is something that's going to come into the universe and then go away. And when it decays into a mixture of photons and other relativistic particles. What constraints are there on a scenario like this? Well, the CMB, the cosmic microwave background, those peaks I talked about, are very sensitive to the photon to radiation ratio, i.e. what percentage of the relativistic particles are photons, as opposed to, say, neutrinos, or any other radiation that does not talk via Thomson scattering to the electrons. And as you can see, the red line here moving around, if you vary the photon to radiation ratio, your CMB changes. And so the CMB is really good at measuring that. The abundance of deuterium in the early universe, as I just showed you, is very sensitive to the baryon to photon ratio. So the abundance of deuterium constrains that. And then finally, the fact that the CMB is a perfect black body spectrum, as far as we can tell, says that any photons that might have been produced via decay like this must have been produced at temperatures greater than 2 keV, as so not to disrupt this spectrum, to give the photons time to re-equilibrize and get back to a black body. You put all those together, and you end up with a pretty tight constraint. So this is the fraction of energy transferred to photons as a function of the maximum amount of energy that this blue, this new decaying particle, injects. And the CMB allows this whole green area. Basically, this is the right mixture to keep that photon to neutrino or photon to other radiation ratio fixed. But then you add in deuterium, and it just clips it all off. No more photons, please. And so this is less than 2%. And so the answer is, okay, yeah, we understand what's going on between these two benchmarks very, very well. That there's no funny business allowed between the CMB and the BBN. Except, we have some evidence that maybe there was some funny business going on between BBN and the CMB. We do have some trouble between the benchmarks. And that trouble comes in the form of a measurement of the expansion rate today, the Hubble constant, which is the value of Hubble today. We can measure this directly by just comparing redshifts to a measure of distance. How do we measure distance? Well, we can use standard candles. So we can get distances from the observed luminosity of stars, supernova, galaxies, that we feel we know their intrinsic luminosities. And here are the types of probes that give you that. So this is supernova, galaxies, other supernova. Those measurements live here. The best is the top one. We can use standard rulers, those acoustic oscillations. That gives us these measurements. Again, consistency. And we can use lensing. We can get distances from the time delays between brightness fluctuations. And those give these measurements. And together, these measurements all prefer a value for Hubble at about the 74 kilometers per second per megaparsec. However, the cosmic microwave background also provides us with a measurement of Hubble, albeit a little less directly. What the cosmic microwave background measures is the angular size of the sound horizon. So this is the distance that sound waves can travel divided by the distance to the cosmic microwave background, the distance that those photons have traveled. The top here is sensitive to the Hubble rate before recombination, before the formation of the CMB, and the baryon density goes into sound speed. The denominator here is sensitive to the energy content after recombination, including dark energy, which gives H naught. So if you put in the known ingredients of the universe, the energy content before recombination, radiation plus matter, the baryon density, you can infer a value of H naught from the CMB. And that's the value up here. And it does not overlap with these measurements. This is the Hubble tension. How do you fix this? Assuming you think it needs to be fixed by theoretical means and not observational means. You try to change the value for the Hubble constant inferred from the CMB. And the way you do that is you increase the Hubble rate before recombination. So you increase this H of z. You have to keep this fixed because this is what the CMB measures. So if you increase this, you must also increase H of z after recombination. And that comes from increasing the amount of dark energy and increasing H naught. So this is the game. What can we add? Lots of new things have been proposed. None of them work perfectly. So you could try adding new relativistic particles, dark radiation. But this N effective, that's that ratio of photons to radiation, that affects the CMB, and you run into problems there. You can put in some early dark energy. Yeah, we don't know what dark energy is. Let's put in some a little earlier and use that. And I'm going to come back to that idea at the end of the talk a little bit more. We wanted to look at, OK, what about a massive particle, a decaying massive particle? Now, it can't be photons. I already showed you the constraint on photons, too much. Let's say it doesn't decay into photons. So let's inject some dark radiation. Now that there's no photon injection, the decay can happen at any time, and I'm not changing the baryon to photon ratio, so the BBN bounds aren't as stringent. This can lead to unique signatures in the CMB. So the black here is what you get from a decaying particle that has a lifetime of 20,000 years. So short by cosmological standards, very, very long by particle physics standards. And that means it's decaying right when the CMB is kind of getting established. And so on large scales, it mimics just extra radiation. So that's the red here, is just normal with extra radiation. And the black mimics the red. But on small scales, it's different. So this isn't just the same as adding different radiation. It has a scale-dependent change in the CMB. And maybe this could help us with the Hubble tension. Except when you put the bounds on it, this is the amount of this new unstable particle versus its lifetime. When you put the bounds on it, you find the amount is now at like the 3 to 4% level. It's still very constrained. Why is it so constrained? Decays that happen before recombination are constrained by the photon to radiation ratio. Decays that happen after recombination are affected by measurements of the baryon acoustic oscillations, basically late time expansion. And you put these all together, and you can't increase the inferred value of Hubble. This is a Hubble constant. Dashed is what you get from just standard cosmology. Red and blue are where you get for before recombination and post-recombination decays. So, I mean, you can edge it up a little, but you can't get up to the values that the direct measurements want. There's just not enough freedom here. It's too tightly constrained. So, lessons learned here. Massive particles that decay into radiation can't solve the Hubble tension. This is actually an example of kind of a more general problem to approaches to solving the Hubble tension. Whenever you want to increase the value of the Hubble constant inferred by the CMB, you're basically adding dark energy to the system. That means you're changing the ratio of matter to dark energy. You're changing the timing of matter-dark energy equality. However, probes of the local expansion, particularly the baryon acoustic oscillations, constrain this ratio really well. So you can't mess with this ratio without messing with these observations. And that's shown here. So this is H naught. The gray is what the value we would want to target to match local observations. The green here is where the CMB lives. You basically need to move this, and you need to move it within this orange band, purple band. These different lines tell you roughly lines that the CMB would be okay with. So if you want to hop from this line up to this line that gets you into the gray region, you have to change the matter density. And so that's difficult to do. And post-recombination decays actually go in the wrong direction. They favor decreasing the matter density. And so it makes this tension even worse. And so the takeaway for this little part of the talk is no new radiation allowed in here. There's nothing, we can be very confident in the fact that the radiation that existed at Big Bang nucleosynthesis is exactly, to within a few percent, the radiation that existed by the time of the cosmic microwave background. Okay, now I want to shift gears a little bit and go earlier in time. So now talking about before the Big Bang, this gap where I am so much less constrained by observations. I mean, I was just at a workshop in Pittsburgh where the common phrase was, this is the wild, wild west. I mean, this era here, anything goes. To put this era into perspective, this is that same plot of the history of the universe in logarithmic scale, the different temperatures today, temperature at neutrino decoupling, temperature at inflation. This whole region here is the gap. So in terms of decades of expansion, this is more than half the history of the universe. So yes, it's only the first tenth of a second, but you're just using the wrong clock. This is the half of the expansion of the universe right here that we don't know anything about. So what happened before BBN? Okay. So we have good reason to think that the universe was not radiation dominated all the way to time zero, whatever time zero might mean. Primordial density fluctuations, those fluctuations we see in the cosmic microwave background, the best way, not the only way, but I'm going to go out on a limb here and say the best way to explain them is to invoke a period of inflation. So this is a period when the universe was dominated by a scalar field that was slow rolling. That means its potential energy greatly exceeded its kinetic energy. After inflation, that scalar field, which we affectionately call the inflaton, may have started rolling fast, a fast roll phase, during which case its pressure would be about equal to its density. We will call this kination. It's kinetic energy dominated. Or it may have oscillated in a quadratic potential, at which point its average pressure is zero, and it behaves like matter. So this could be a kination period or a matter-dominated period. Other scalar fields or particles could also have come to dominate the universe in this time. Remember, we have a lot of expansion time to deal with here. This is actually a well-known problem in string theory, the string moduli problem. String theory has all these extra oscillating scalar fields running around, and actually making them not dominate the universe before BBN is harder than letting them dominate. They can also generate periods of kination. And the fact that we haven't seen dark matter yet in any sort of direct detection or collider experiment has generated interest in these so-called hidden sector dark matter models, in which case there is a second particle. So you have a dark matter particle, X, that talks to particle Y. Particle Y can decay into the standard model, and these Y particles tend to dominate the universe during this period. So we've got a gap here. I'm going to say let's fill that gap with either an early matter-dominated era or a period of kination. So to put this in perspective, what does this mean? Early matter-dominated era, the dominant component of the universe is going as matter. So it's redshifting away, the density is going as 8 to the minus 3. This has to end somehow. We have to get radiation domination in time for BBN. It ends when this dominant component decays into relativistic particles. A period of kination, the energy density goes as 8 to the minus 6. That's faster than radiation, which means this will come to an end all by itself. It doesn't need to produce any new relativistic particles. It will just become subdominant to radiation without any interference. It will naturally end. What does this do, putting this so early in the universe? This has implications for dark matter production, early structure growth, and you put those two together to make enhanced dark matter annihilation rates. So let's go through each stage of that. How do you make dark matter? My favorite way to make dark matter is thermally. Let's start with a hot radiation bath. We know we've got one of those in the early universe. Let's make dark matter that way. So, recipe number 1, freeze out. You start with a bunch of hot particles. I'm going to say photons here, but any hot particles will do. Your coupling is up to you. And these particles are hot enough that they can pair produce your dark matter. Now, of course, your dark matter can also self-annihilate back into those hot particles, but this is going both ways in equilibrium. Now, those particles are cooling as the universe expands, and eventually they become too cold. Their temperature falls below the mass of the dark matter particle in the appropriate units. That pair production stops, but annihilations continue. So the annihilations continue. The dark matter density falls exponentially. Eventually, it becomes so diluted that those self-annihilations stop because the dark matter particles just simply can't find each other anymore. This happens when the age of the universe falls below the time between collisions. At this point, we have freeze out, and the dark matter that is left at that point persists forever. The remaining dark matter, its abundance is inversely related to its annihilation cross-section, matches observations for a cross-section on the order of 10 to the minus 26 centimeter cubed per second, which in units that might mean something more to a particle physicist, a few hundred GeV particle with a coupling strength on the order of 10 to the minus 3. These are our WIMPs. Weakly interacting massive particles. The numbers work out nicely. Not perfectly, but nicely. There's another recipe, another flip side of this, the feebly interacting massive particles, where dark matter is created via pair production but does not reach chemical equilibrium. And the thermal bath becomes too cold for pair production at some point, and then you're just left with whatever you were able to pair produce in that time. These are generally much, much smaller cross-sections. Now we can then, in this idea that dark matter is a thermal relic, there should be an equal amount of dark matter and anti-dark matter in the universe. In many models, it is the one and the same thing. And so those dark matter particles can collide, annihilate, and make things that we can see. And so if you simulate what the gamma ray sky should look like, all the places in the sky, this is the galactic center, lots of dark matter there, and then we've got some satellite galaxies. Every place in the sky that has a lot of dark matter should light up. So we go out and we look, and this is what the gamma ray sky actually looks like. And yeah, there's a lot of gamma rays coming from the galactic center. Problem is, you know what else emits gamma rays? Neutron stars. So the gamma rays are mostly coming from the plane. This could be astrophysics. What we're not seeing yet is any hint of dark matter from some of these like isolated dwarf galaxies that aren't showing up yet. So we haven't seen this yet. And as a result, the standard story I just told you is ruled out for dark matter particles less than a few hundred GeV at this stage due to these observations. But I want to convey the message that this standard picture I just told you assumes something about what the universe was doing before BBN. And we don't know what the universe was doing before BBN. So there's two assumptions that go into that calculation. One is that the Hubble rate is just a function of the standard model temperature as determined during radiation domination. The other assumption is that no new photons were created after dark matter freezes in or freezes out. Both of these assumptions can be relaxed in the presence of an early matter-dominated era. So increasing H at freeze out leads you to freeze out a little earlier, and that leads to more dark matter, like in the red curves. To recompensate, you need to lift the annihilation cross-section, so you get rid of the excess dark matter. Conversely, photon injection dilutes the dark matter abundance, meaning you have to take the annihilation cross-section down for freeze out or up for freeze in to get the right relic abundance. So this shows cross-section versus mass, and these are different early matter-dominated eras. That these different early matter-dominated eras, the actual cross-section you want to get the dark matter we see today lives on these curves. Notice these cross-sections are a lot smaller than my 10 to the minus 26 centimeter cube per second number I gave you before. In fact, the situation can get even worse. If you're willing to say that a radiation-dominated era existed prior to the early matter-dominated era, then these different curves show for a fixed end of the early matter-dominated era. All these curves can give you the right abundance today. So my takeaway here is, you give me a particle, I can cook up an expansion history that makes that particle the dark matter. No problem. So you should look for everything because it's wide open. However, do notice that all these cross-sections are a lot smaller than the number I originally gave you. This was widely thought to be a nightmare scenario. We'll never detect this. But not so fast. Because an early matter-dominated era has another consequence. It speeds up the growth of density perturbations. So this is showing the density fluctuation in dark matter compared to its initial value. And for every wavelength, what happens is it's fixed. It enters the horizon, basically becomes causally connected. And during an early matter-dominated era, it can grow linearly with scale factor. And then it slows down and starts growing logarithmically with scale factor after the universe becomes radiation-dominated. This little head start in structure growth, this little boost, radically changes the amount of dark matter in halos with mass less than the mass within the radius at which these enhancements happened. What scales are we talking about here? If the early matter-dominated era ended, that's this reheat temperature, at a temperature of 1 GeV, we're talking about sub-Earth mass. So these are really small objects. These are microhalos. Now, dark matter is not perfectly cold. Dark matter has some random thermal motion. Now, what does that random thermal motion do? If I have a bunch of dark matter particles here that are randomly moving around, and I consider that I have an overdense region of this size, this yellow circle here, I move all my dark matter particles around, and they move by this much as the arrows. The dark matter particles in this region generally stay in this region. Nothing happens. But if my region is smaller, then these little dark matter particles will exit this region, and I won't have an overdense region anymore. So free streaming of dark matter basically erases fluctuations on small scales, scales smaller than the free streaming length. You put these two effects together, and this shows up in the matter-power spectrum. So I'm going to show this a lot. Let me explain what this is. This is the matter-power spectrum. This is the average amplitude squared of density fluctuations as a function of inverse wavelength. Remember I told you cosmologists do everything backwards? So these are big wavelengths. These are small wavelengths. An early matter-dominated era starts an enhancement. These are the modes that are small enough that they entered the horizon during the early matter-dominated era. They get this extra growth. You get a bump in the power spectrum. The cutoff from free streaming cuts this off. So this is the cutoff due to free streaming or any other effect. The ratio of these two scales, the scale of the end of the EMDE and the cutoff, determine how big your bump is in the matter-power spectrum. How much extra inhomogeneity do you have? If the WIMP dark matter couples to the standard model during the early matter-dominated era, this ratio is generally less than 80. So I'm showing three ratios here, 40. I'm showing 40 and 20 here, ratio of the cut scale to the reheat scale. If dark matter is in a Hidden sector, it's much, much colder. And so the cutoff is not set by the dark matter. It's set by the thermal properties of the particle that dominates during the EMDE. What does this do? This is the fraction of dark matter bound into halos, small little clumps, as a function of time, redshift. And for these different cut ratios, you can get most, this is over half of the dark matter bound in these tiny little halos at extremely high redshifts in the hundreds. For context, without an early matter-dominated era, you don't get any structures before a redshift of about 50. With Hidden sector dark matter, we can even go earlier to radiation domination. You could actually start forming halos during the radiation-dominated era. However, there is a limit here. If you actually form halos during the early matter-dominated era itself, those halos predominantly consist of the unstable particle. And when that particle decays, those halos are going to evaporate. And the dark matter particles that were in there are going to be released. And that adds more thermal motion to your dark matter. It basically heats your dark matter. So there is a limit to how much enhancement of structure you can get. How do we observe this enhancement? So this is a simulation my group did of one of these enhanced small-scale spectrum. You end up with a bunch of little clumps in this simulation. Dark matter is mostly bound into these little clumps. Those little clumps determine how likely it is for two dark matter particles to find each other and annihilate. And that is what we call the boost factor, which we can predict using the properties of these little clumps. We predict how much, by what factor, it becomes more likely for dark matter to collide and annihilate because dark matter is clumped into these tiny little microhalos as opposed to being smoothly distributed. And the numbers we get are quite profound. So this is work that's coming soon, led by my graduate student, Juan Bay. This is the boost factor. This is the enhancement to the dark matter annihilation rate due to the presence of clumps as a function of redshift. Without an EMDE, this purple line, you start picking it up at a redshift of 30, and it grows to about a factor of 10 to the 6 today. With an early matter-dominated era, it starts picking up at a redshift of 1,000 or earlier and can be 6 orders of magnitude higher today. This can compensate for the lower annihilation cross-sections you need in these scenarios. So you get you win some, you lose some. You need a lower annihilation cross-section, but you get a much higher annihilation rate due to the clumpiness. And you put these together to make constraints. So one thing you can do is look at the intergalactic medium temperature. This dark matter in these clumps will heat the IGM and form an uptick in temperature as a function of time. This is the cooling of the universe, and then the little microhalo annihilation within the microhalos start heating it up. You can put constraints on this from hypothetical measurements from 21 centimeter. However, the best constraints, that's these solid lines are from 21 centimeter, are somewhat futuristic detection of 21 centimeter absorption. These dashed lines down here are current bounds from isotropic gamma ray background. So it seems that is the best bounds. And these are work done by my former student, Sten Dellas. What type of EMDEs does this constrain? If you plot this as a coupling between the particle that is decaying and the standard model, so this is a proxy for decay rate, and dark matter mass, if the decay rate is too short, you don't get an early matter-dominated era. If the decay rate is too long, you run into Big Bang nucleosynthesis, and you can't do that. Gamma ray observations basically constrain a middle ground where it's long enough, but not so long that gravitational heating destroys all your microhalos. And so these are the type of constraints you can get. I'm going to skip that and go into kination a little bit. Dark matter production during kination is a little different. There's no entropy injection. So you actually need a larger cross-section during kination. The numbers you need are to get the right relic abundance. So this is the right relic abundance. This is the actual relic abundance. The intersection here is at larger cross-sections. So these are highly constrained. They're even more constrained when you confront the fact that dark matter fluctuations actually grow faster during kination than they do during radiation domination. This is a little weird. You wouldn't necessarily expect gravity to be more powerful during kination. There's a lot of pressure present during kination. Gravity is not doing this. But this isn't gravitational growth. So this is the density fluctuation of dark matter. It grows during kination and then slows down during radiation domination. What's really happening here is the particles are drifting. So the amount of distance that a particle can travel is related to the Hubble rate. And that is logarithmic in A during radiation domination and linear in A during kination. And so you can get structure this way. And I'm going to skip the constraints to say, what about now after BBM? So going back to the Hubble tension and scalars and kination. Remember our goal, shifting gears now to the later universe. Our goal was to solve the Hubble tension by increasing the energy density in the early universe. The problem we ran into before was, where does the added energy go? It can't stick around as dark radiation. It can't stick around as matter. The solution: the energy density in a rolling scalar field like kination dilutes faster than radiation and can effectively disappear. And this is one of the more popular approaches to trying to solve the Hubble tension. It goes by the name of early dark energy. What we're doing is adding a component. So this is energy density versus today. Here's dark energy down here in the green. Here's radiation in orange, matter in blue. And we're going to add this extra component that holds steady and then decays faster than radiation for a while. To solve the Hubble tension, this needs to compose about 10% of the energy density of the universe and redshift away as a to the minus 4.5. So just slightly faster than radiation. However, if you have a scalar field that does this, and let me say, just a note, Stefan and collaborators have had something to say about, does this really solve the Hubble tension? Here's Hubble, the posteriors. The red here is what you get from the just CMB data alone. You actually need to fold in measurements of the direct rate, this gray, to pull it up. It would really rather not. So to the extent this actually works is a bit under debate. But it can get up there. It's just, it doesn't really want to. You have to force it. However, we are told by the high-energy theorists that there are lots of scalar fields probably around in the early universe. This goes by the name of the axiverse. Many axion-like scalar fields, all with different masses and potentials, that each could come to dominate the universe for a little period of time. Early dark energy could be one such episode. Our current era of dark energy could be one such episode. What other episodes could there be? And so could we have something that came to dominate the universe and then redshift away quickly, like kination? How constrained is this scenario? This will give us kination. And can it enhance structure growth? Can this actually lead to earlier structures in the universe? And the answer is yes. So this is a complicated one. Let me take it through slowly. This is Hubble. And so what Hubble is doing relative to standard is it's matching, and then it grows for a while, and then it falls for a while. This era here of it growing will be a slow drift era. This era of it falling will be a fast drift era. For context, early dark energy to solve the Hubble tension happens much later over here. So we're putting this much earlier in the universe. As a result, we can make it a bigger bump. This shows you how different density modes that enter the horizon at different times are affected by this. So example, for the purple, it comes in, and then if it were standard, it would follow this dash trajectory. But because it's inside, it's affected by this slow drift, it stalls, and it ends up suppressed. And that ends up with a suppression over here. A mode that enters in late, like this green, enters in during the fast drift age. But notice it enters in later. It gets a late start. It goes faster after that, but it can't quite catch up. And it also ends up suppressed over here. In the middle, you have like the orange mode here that actually gets this fast drift growth and ends up enhanced. And so you end up with a peak in the matter power spectrum, a boost to structure. You can change the amount of very early dark energy, and that just makes your enhancement grow or shrink, depending on how much of this stuff you have. If you try to change the axion mass, i.e. change when does it start to roll, you change the position of this peak. You also change, the pink here is, these are the scales that the CMB sees. If you put this too late, you're mucking with the cosmic microwave background. It doesn't like that. It's unhappy. You put it a little earlier, and now it's okay. And you can adjust the peak height and peak location this way. So what's actually allowed via data? This shows how much very early dark energy you have, and when does it start to rule. Everything over here starts to roll too early. It's ruled out by BBN. Everything here starts to roll too late. It's ruled out because it affects the CMB. There's a sweet spot here where we did a separate analysis to kind of zoom in on this sweet spot where you can get order of magnitude. This is saying it's increasing the Hubble rate by a factor of 50 or more. Order of magnitude changes in the Hubble rate happening at a redshift of about 10 to the 7, or a scale factor of 10 to the minus 7. These dots here show different scenarios within this allowed region, and here's the power spectrum that results. What you end up with is an enhancement on the scales of dark halos, and a suppression on scales probed by the Lyman alpha forest. So this is a really unique and interesting signature in the matter power spectrum that is just at the cusp of detectability right now. And I think that's really exciting. All right, so I want to wrap up here with my little summary of dark probes of the early universe. That both, if you change the expansion rate here in the gap, you change the abundance of dark microhalos. And those dark microhalos can be constrained via their effect on dark matter annihilation. If you want to solve the Hubble tension, a good rule of thumb is don't leave any dark radiation behind. You want to do this with some kind of scalar field. And those scalar fields, when they're put in early enough, can lead to some really distinctive imprints on the matter-power spectrum that will be probed by dwarf galaxies in the near future, while also suppressing power on slightly larger scales, which is an interesting thing because there is some evidence that the universe would like that. And that's where I'll end. Thank you. Microhalos, yeah.
So one of the things you discussed was more dark matter annihilation. Follow that. Are there other effects that you thought about that you might get from the microhalos? I mean, it sounds like kind of a hard thing to find.
Yes. Futuristic. But there are some, not very, moderately. So there are some ways you could hope to detect these things gravitationally. Now, I remind you, these are Earth mass or sub-Earth mass objects, and they are halos. They're diffuse. They're not primordial black holes. So they're kind of solar system size. So they're puffy. Even so, there have been some excellent work done on how could you possibly detect such a thing. Pulsar timing arrays, not current, but not so distant future either, decades in the future, say. Could constrain the population of such objects because of the way they would gravitationally tug on pulsars and affect the timing of their arrivals. And there's been some really great work done by Catherine Zurich's group, and my former student, Stan Dellis, again, had a great paper on this. There's another interesting idea that's been thrown out of if you have a cluster and then you have stars, background stars, going through caustics of that cluster, microlensing, those stars will be very heavily magnified. And that means any perturbations to the gravitational field will be also heavily magnified. And you can look in the scatter of that microlensing light curve, you can detect Earth mass objects. Again, futuristic, but not, decades future, not centuries future. So there is definitely work ongoing on how to detect these things gravitationally. We're not there yet, but in development.
So one of these you were showing was that you could suppress the Lyman alpha structure and not monkey too much with the galactic scale, but at the cost of a peak that's quite sharp at smaller than galactic scale.
Mm-hmm.
Would you think this things like stellar streams?
Absolutely. So these peaks here enhance the abundance of dark halos. These are halos that we wouldn't necessarily expect to host stars or baryons. Between the masses of 10 to the 6 to 10 to the 9, that is exactly the sweet spot for streams. So this is a very interesting signature for streams. For context, as part of just, why I find this so cool, a lot of people talk about suppressing small-scale structure and suppressing galactic structure on these scales. Not many people talk about enhancing it. There aren't many ways to enhance it. This is one. And yes, streams would have a lot to say about exactly this population of halos. So that's a very exciting avenue for potentially detecting something like this.
It's not a question, it's a comment. Professor Erickcek will actually be around tomorrow. And you're all welcome to go up and chat, talk physics. We know a lot of stuff. We learn a lot. Room 633. And if you can't find her there, she'll probably be in the theory lounge with the various different. And then my other question, now I have a question. So tomorrow she'll be around. My question is, any person that works on dark matter comes here, somebody's got to ask this question. Do you have a favorite dark matter?
I mean, I do. I really like thermal dark matter. And I like it for two reasons. I find it the nicest, most compelling way to make dark matter. It's easy. It's inevitable. You've got a hot radiation bath. We know we have a hot radiation bath in the early universe. Let's make dark matter that way. It's also optimistic. To make it this way, it has to talk to the standard model somehow. And so we have hope of detecting it non-gravitationally. And, I don't like dark matter particles that don't interact at all except via gravitation, because how will we ever fully identify it? So I still have hope for thermal relics. But as you saw, I guess one of the takeaways I wanted to say is that broaden your definition of thermal relic. Thermal relics are not pinned down to one mass and one cross-section. Thermal relics can live anywhere you want them to live, including regions that I have seen experimental particle physicists sometimes rule them out as overclose the universe. No. Nothing overcloses the universe. I can dilute anything. So, there is no forbidden region of overclosing the universe. You find me a particle there, I'll make it work. Don't worry about it. You just told me something. You find me a particle there, and you just told me something really interesting about the expansion history of the early universe. Thank you for that. So, don't limit yourself by, we don't know what the early universe was what was going on in the early universe. Any thermal relic, anything that is pair produced, we can make it work.